Hey guys, so today we are going to discuss of the question called as validate binary search tree. So this is a Leetcode medium question. So as the title itself says, validate binary search tree. So that's what we're going to do. But still, let's start reading the question. So given the root of a binary tree, determine if it is a valid binary search tree. So let's know what is a binary search tree. Let's try to do that. So for example, let's take an example. Let's assume we have this kind of a tree which looks like this. So here we are having a tree which looks like this, right? So here it contains some values, right? Like 5 1 4 3 6, right? So this is a tree, this is a binary tree. So what makes a tree a binary search tree? So let's know that. So a binary search tree is nothing but all the values to the left subtree should be less than the root, and all the values to the right subtree should be greater than the root. That's the main condition. So what I'm trying to say is, so left should be less than root and right should be greater than root. This is the main condition. I know you didn't get much with this condition. Let's try to see with this tree. So if you see clearly, in here, if you have, for example, let's take we are at 5, we're at here. So all the values towards the left of 5 should be less than this 5. So in this case, the value which are left to 5 is just 1, right? So 1 is definitely less than 5. So this satisfies. Now let's come towards the right. So all the values towards the right are 3 4 6, right? So all the values towards the right are not greater than 5, because there is a 3, right? 3 which is towards the right of 5 is less than 5, but all the values towards the right of 5 should be greater than 5. And also 4 as well. 4 also shouldn't be in the right side of 5. So in this case, this is not a valid binary search tree, because these conditions are not satisfying. So this is not a valid binary search tree. Not just, here, not just considering this main root of the tree. For here also, for example, let's take this is the root, right? So the left side there is only 3. The 3 is definitely less than 4. This satisfies. Coming to right, it is 6. 6 is greater than 4. So if we consider this tree, if I consider only this subtree, this subtree is a valid binary search tree, because this tree is satisfying the binary search tree conditions. So this is a valid binary search tree. But coming to the main tree, which is rooted at this 5, this is not a valid binary search tree. So that's where we have to return false. This is not a valid binary search tree. So now let's see how a valid binary search tree looks like. For example, let's take we're having this kind of a binary tree, right? We're having this kind of a binary tree which looks like this, right? So now let's try to see if it is valid or not. So starting from 5, so what I can do is I can see all the left side elements are smaller than root and all the right side elements are greater than root. So in this case, all the left side elements are 3 4 and 2. So 2 3 4. So all the elements 2 3 and 4 are less than 5 for sure. So we can that condition satisfies. Now coming to the right side, which is 8 and 6 and 9, right? So 6 8 9 are definitely greater than 5, so it satisfies. The binary search tree which is rooted at 5 satisfies this condition. So coming to the next node, which is 3. So the reason why I'm trying to coming to see for each and every node, or I mean why I'm trying to see for each and every node whether it is a valid binary search tree or not, is for example, when we have seen from 5, it is verified that it is a valid binary search tree, right? So now what if, for example, let's take we didn't see the bottom nodes or the subtrees, and we just clarified or we just finalized this is a valid binary search tree. So for example, I would just make a small change for this tree. Maybe I changed it to 2 here and 4 here. I mean, maybe not 3 4 like this. Maybe 4 here and 2 here. So now let's try to recheck from 5 again. So now all the elements towards the left, which are 2 3 and 4, are less than 5, right? And all the elements towards the right 6 8 9 are greater than 5. So now it is satisfying here. But if you see here, when it comes to 3, all the elements towards left, which is only 4 in this case, is not less than 3, because if it is towards the left it has to be definitely less than 3, but here 4 is towards the left of 3 but it is greater than 3, so it doesn't satisfy. So that's the reason why we have to check for each and every node, for each and every subtree. So that's the case. So now let's change it. So this is the tree which we have before, right? So let's erase this as well. So now again coming to 3, let's check from 3. So all the left side elements are 2, all the right side elements are 4, so this satisfies. So coming to the next, which is 2. So all the left doesn't have any left elements, so that's okay. Let's check the right. It doesn't have any right elements, that's okay. So a tree which has only one node or one value is always a valid binary search tree for sure. So coming to the 4, it's the same case. Now again coming towards 8, towards the left of 8 it has 6. 6 is less than 8, that satisfies. Coming towards the right, which is 9, 9 is greater than 8, this satisfies. So that actually means if all the subtree satisfies the valid binary search tree, then that actually means the entire tree is a valid binary search tree. That's the case. That's how you have to find, that's the main case. How will you find a tree is a valid binary search tree or not? So now we have done this manually, right? We have just used our human brains and try to see if it is a valid binary search tree or not. But logically, programmatically, how can we do that? So let's take the same example and let's see how can we do that. So one programmatical approach would be, so if you see clearly, the left subtree max should be less than the current node, right? And the right subtree min should be greater than the current node. Those are the case, right? So what we can do is, for each and every node in the tree, we can see the max of left and the min of right subtrees and see if it satisfies or not. So the condition would be like this. So the max of left, the max value of the left subtree should be less than the root, and the minimum value of the right subtree should be greater than the root. So what we can do is, one approach, for each and every node we can just do brute force. For example, let's say if I'm at 5, I can traverse the entire left subtree and find the max value, and for the entire right subtree I can find the min value and just compare that. And again coming to 3, I'll go to the entire left subtree and just find the max value, entire right subtree I'll find the min value and compare this. I'll just do these validations. So that would be one approach. So as we're trying to do each and every time, for each cell we're trying to go towards the entire downwards tree, right? So for n cells approximately, for example, let's take we have a skewed tree like that, like this which looks like this, right? So now in this case we have to do, for each cell we have to go downwards like that. So in this case we roughly take it as order of n square time complexity, right? So the time would be order of n square in these cases. So this is pretty much a brute force approach, right? It's not recommended. So there you can make this a small optimization in this. Instead of doing this as order of n square, I can maybe make this order of n. So what I can do is I can start from the bottom by doing posterior traversal. I can start from the bottom and send the max of the current root. In this case it is only 1, right? I can just send 2 towards the top. So in this case I can just send 4 towards the top. And as the left subtree is just only 1 and right subtree is just only 1, so 2 is less than 3 and 4 is greater than 3. So it satisfies. Now what I have to do is, I have to send the max of these threes. I have to send the max. So in this case 2, 3, 4, the max is 4. I'll be sending the 4 towards the top, and coming to the left again, I'll be sending 6 from here. I'll be sending 9 from here. So here in this case 6 is less than 8 and 9 is greater than 8. It satisfies. Now I'll be sending the minimum of these 3. It's going to be 6, right? So now 4 is less than 5 and 6 is greater than 5. It satisfies. So this is one approach. So as we're trying to start from the bottom and we are reaching the cell, or I'm reaching the node, or I'm reaching the root of every root only once, right? So that's why it's going to be order of n. So we have optimized order of n square to order of n, right? This is one approach. But what I would recommend, one approach is, there is a fun fact with binary search tree. What it is, for example, there are three kinds of traversal, right? In order, post order, and pre-order. So in a binary search tree, if you perform an in order traversal, the order of elements will definitely be in ascending order. See, for example, let's try to perform in order in here. So in order is nothing but the left and the root and the right. This is the order, right? First we have to traverse the left subtree, and then we have to come to root and traverse the right subtree. So in this case, let's go to the left. Let's go towards the left. It doesn't have left subtree. Now it's going to be 2. It doesn't have right. So go towards 3. Now it's 3. Similarly, it's going to be 4. 5, 6, 8, 9. So if you see clearly, this is entirely in ascending order, right? So if you perform in order traversal in a binary search tree, it is going to be an ascending order. And if you have the ascending order, you can easily see if the left one is equal to the right one or not, right? That's it. So now what you can do is, if you get this order, what you have to make sure is you just have to see if this is in ascending order. If the values are not in ascending order even after performing in order traversal, then that's definitely not a valid binary search tree. That's the main intention, that's the main case for this approach. So let's try to take the same example and let's do that. So what I can do is, first one way was just as I said before, I'll be storing the in order traversal in a list maybe, and just see if the previous value is less than the current one, or let's just see if it is an ascending order or not, right? So for that it would take an extra space, right? We have to store the ascending order in a list, maybe store in the array list, and just see the previous value, which is this value, is less than the current value. If it is satisfies, if that satisfies, then just go towards the right and just see if the previous value is less than the current value. That would be one approach. But as you're trying to use an extra space of list, right? So what we can do is, instead of storing them, right, we are trying to do in order and trying to store them and see after that, right? So what we can do is, maybe I can not store this and just verify even during traversing only. So for example, what I can do is, imagine I am at 5. I am trying to perform in order traversal. So I'll come here and doesn't have left, right? So currently the previous value is null. Imagine like that. So now until now we have not come to any root. We have gone towards left, it is null. We have come back to 2. So in this case, this is the first element, first in order traversal element, right? So now as the previous value is null, we can consider this as true for now. Like we can just add 2 for the in order traversal. So now we have to change the previous value to 2 now. So it's going to be 2. So now going towards the right, so it doesn't have any right element, so we can just come back again, right? So this is 2, you can come back. So now from 2 we have to go to 3. So we have come to 3. So now the previous value is 2 for now, right? For 3. So we have to see if the previous is less than 3 or not. It is less than, so it satisfies. So what we have to do is, we have to change the previous value to 3 now and go towards 4. And also we have to add 3 for the pre-order. I'm just writing the order of our in order traversal. So we have come to 4. Though before 4 we have visited 3, right? So that actually means 3 is less than 4, so it satisfies. So I have to change the value to 4 and go back to 3. So we are done with this subtree. Now I'm going back to 5. So the previous value which we have visited before 5 is 4. So 4 is less than 5, it satisfies. So now I have to change it to 5. I have to go to the next. So I'll come to 8. I'm coming to 6. So it doesn't have left. Coming to 6 back. So now the previous value before 6 is 5, which is less than 6, right? So it satisfies. I'm changing it to 6 and going back to 8. So now the previous value is 6, which is less than 8. It satisfies. I'm changing it to 8. I'm going back to 9 now. Listen carefully, I'm trying to do in order traversal here. That's why I'm first trying to traverse the entire left subtree, coming back to root, and again going to right subtree. So that's the main intention. So now which I'm at 9, the previous value which I have visited is 8, right? Which is less than 9, so it satisfies. Now I'm coming to 9. So now as I've done with 9, I'm done with 8, I'm done with 5 as well. So that actually means I'm done with entire subtree or entire tree. So in this case we didn't get any conflicts, right? We didn't get any case where previous is greater than the current one. If that happens, then that's not a valid binary search tree. So this is the approach. So previously we have tried to store the in order traversal in the list and try to see the previous value is less than the current value. So in this case what we have done is, instead of first storing them and seeing that, we are just checking during the traversal itself. So that's the main optimization between those two. So now let's try to implement this approach. So here we're having a method called as isValidBST. So it passes a root of the tree. So we have to verify or we have to validate if that root or if the tree is a valid binary search tree or not. So first thing what I'll be doing is, I'll be seeing if root is equal to null. If it is null, I'll be returning true, because an empty tree is also considered as a valid binary search tree. or else I have to see the left subtree because we're performing in-order traversal, right? So what I'll be doing is, if not valid, if not is valid BST of root dot left, I'll be returning false. I'll tell you why, what happens. I'll tell you what it is performing. So now for I'll be creating an extra variable to see the previous value, to keep track of previous value. So it's going to be a global variable. So initially this is a reference type, right? This is a reference type. So it's going to be null initially. So when I have done with the entire left subtree and I have come to root, right? So what I'll be checking is, if prev is not equal to null and prev is greater than or equal to root dot value, then I'll be returning false, or else prev will become the current value. Now I'll go to the left subtree. If not is valid BST of root dot right, return false, or else at the end return true. So what I'm trying to do here is, I'm going to the left subtree, and if at all any case I get it as false, and I don't have to check the remaining tree, right? Because once the condition doesn't satisfy, once if this condition doesn't satisfy, then I can just return false to the top root, right? I don't have to check the remaining tree. If it satisfies, then I can proceed with the downward tree, the remaining subtree, right? Again, this is what I'm just assigning the current root value to the prev, so that I can see the previous value is greater than or equal to current value in this case. So this is pretty much the implementation. Let's try to run this code. Yeah, it worked. Let's try to use some extra test case as well. Yeah, let's try to submit this. Yeah, it got succeeded. So the main intention was here is I have just done in-order traversal, because in a binary search tree, if it is a valid binary search tree, then if you perform in-order traversal, then for sure it has to be in ascending order. So that's the main intention here. So we just have done the in-order traversal and just saw the previous value is less than the current value. If that satisfies for the entire tree, then that is a valid binary search tree, or else it is not a valid binary search tree. So yeah, this is the video. If you like the video, please make sure you like and subscribe. Thank you.